Okay, so I'm going to review a few things because this is basically part 2 of the items that we started to talk about yesterday. So this is still module 5. So we moved forward just a little bit and we got to like, we started to get to kind of validations, and we're gonna continue through that. Okay. So we talked a little bit about algorithms yesterday. So you had these great like kind of visuals around the algos, right? So supervised learning, then we had unsupervised learning, right? This is where PCA and IP insights and random cut forest and all that. And then text, like sequence to sequence, again, LDA shows up again, blazing text and sequence to sequence for speech. And then last for image to videos. And I want to be clear, I did mention yesterday that I at least did not see any ResNet or like most of this section, like the only thing in this entire thing that was actually on the exam was the deep AR for time series forecasting. That was it. So I don't know if that was an aberration. And don't get me wrong, they talked about some semantic segmentation. They talked about object detection. They had you understand what those type of algorithms do, but they did not actually have any questions on FSN, PSP, ResNet, or any of the others, any variation, right, on the exam. I don't know why that is. Maybe that's, it doesn't, that's not relatively new, so I'm not sure what's going on there. And then we talked about formatting data and about how protobuf is, so this is something to know, and you have to remember this for the exam. Protobuf is typically 6 times faster than comma separated values. And like a file format like Parquet, P-A-R-Q-U-E-T, Parquet is typically faster, 6 times faster than CSVs. So be aware that these structured file formats that you can convert your data into, they are typically way faster than using either TSVs or CSVs for data structures. So the reason why Amazon's going to harp on this, and this was true well before Amazon had any of these services, is that they're going to ask you questions like, what's the best file format and S3 mode to run it in? And I hope you're really listening, because they asked me several questions on this. And the best file format is in order of speed is going to be either Record IO Protobuf, or just Protobuf is what they'll call it, or Parquet. And then, you know, CSV is going to be last, right? So whether they're asking you about Athena or about SageMaker, I don't think Athena actually can read Protobuf, but regardless, Parquet and Protobuf are going to be your preferred file formats. For SageMaker, it's going to be Protobuf. For Athena, it's going to be Parquet. Okay, so just know that like file, like how you structure these, they're going to ask you questions about this. Now, as far as S3 modes, file mode is where it copies the entire file to the local EBS volume. And I know some of you were asking about this before, but file mode, where you're using S3 as a data source, means you're going to copy the file out. And once you've got the file, then you're going to start processing the data set. If you put it in what's called pipe, P-I-P-E mode, and it's especially if it's in protobuf format, it's just going to start streaming portions of the file, and it's going to start processing it as it's streaming it. Okay, so just remember that for the exam, is that pipe mode and any other format other than CSV is typically going to be faster. So protobuf is the preferred. Okay. So pipe mode is going to be way faster than file mode. Just to be clear, pipe mode is going to bypass EBS. So it's going to load it straight into the application. Keith, I hope that's clear. File mode uses EBS, pipe mode bypasses it by streaming directly into the app. Yeah. Obviously, if you don't want to use EBS, by the way, you could use EFS or Lustre, right? Pipe mode, Dakota, that's a good question. So pipe mode is actually available for CSV. I just want to tell you that on the exam, I was a little bit like, they keep asking me questions like they think that pipe mode isn't available for CSV, but I think it's been available for CSV since like 2018. So I was a little weirded out by those questions, but bottom line is that pipe mode is available for CSV, but that's not preferred. Protobuf is preferred, but you could use pipe mode for CSV as well. Yeah. All right, and then we talked about how, you got to remove the headers and you have to put your label, not your features, your label at the front of the doc in column 0, right? When you want to submit to SageMaker. And then if you're using Python, you were cool, but if you want to use other languages, make sure you download the latest protobuf definition file, right? And then we were on to splitting data and cross-validation. So any questions about anything that we covered yesterday? Cool. All right. And then now what happens is that after pre-processing the data, right, you want to decide how you're going to split your data. Oh, sorry. Let's stand up. See, that's when I know I'm healthy, because I feel like standing up a little bit. Okay, so pre-processing your data, want to figure out how to split your data. All right, so someone tell me what the standard splits are. What's a typical split whenever we're looking to split things up into training? It says evaluation, by the way. That's also could be called validation data. And then it says testing at the bottom. Sometimes it's referred to as holdout data, just so we're aware. 80-10-10, good. What's another common split? If you have enough, right? Yeah, 70-30, 80-20. Yeah, good. And the 30s and the 20s, by the way, then get split, right, between the validation and the test data or holdout data. Tyler, I haven't seen that one, but again, plus or minus 5%, depending on your data set, isn't necessarily going to make a big difference. Yeah. So just remember the alternate names. I think these are the names they use. Although I got to tell you, I think evaluation is a mistake. I don't think I've ever used them use evaluation data on the exam. I think it's always validation. So they might use the word evaluate with your validation data, but I don't think that I've seen the word evaluation applied. It's usually training, validation, and testing data. Now, which of those are used in the training mode? Like when you're actually like teaching the model, which of those are used? Good, 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 good. Right? And then the testing data is just used, right? Typically with no labels, right? Just to make sure everything's cool. Like, all right, we got everything trained. Let's see if you're ready for production. Let's see if you're good enough, right? And then, it's almost, I wish there was a fourth one here, because then there's like real world, like production data, right? Because you still have to check it once it gets into production, right? Now, sometimes you'll make predictions and you'll get immediate results, like the customer will buy, for example, the ad that you're doing. And sometimes there's a longer cycle where you're like, we got to wait a month for all the camera data to come in and take a look at it to make sure, right? So, all right, so why do we split the data? Okay, here's the deal. If you evaluate a model on the same data that it trained on, if you try to validate it, what will happen is that it's going to overfit, which is going to be discussed later on. But basically what that means is that it's basically memorized the training data. It's not really doing analysis, right? So for now, just know that overfitting is basically where it learns the particulars of a data set like too well, and it's not really doing analysis, it's doing memorization. We have experienced that as people. How many times have we memorized the answers to things, but didn't really necessarily understand what it was doing, right? We couldn't actually do the analysis. I can't remember the name of, can't remember the name of that learning rubric, which talks about like, like memorization. It's like the 7 steps of like mastery for a topic. So essentially, by the way, overfitting is just memorizing the data, as opposed to really learning the like relationships, the features, the aspects, the characteristics, and then allowing the model to learn what those relationships and patterns mean and apply that to new data and therefore derive proper predictions. So overfitting is a problem. The other problem, obviously, is that if you don't give it enough data, obviously, right, then it's not going to be able to cogently learn as well. And so in other words, it can overlearn, it can underlearn in a sense, right? So you've got overfitting and you've got underfitting. We're going to talk more about that. So just pause on those definitions for a minute. But this is why, for example, we want to split the data, is we want to teach it some things and then we want to basically test what it's learned. And if you use the same set of data, that can be problematic. Now, there are ways though to vary this. So you could end up using the same data, especially if your data set's super small, right? Now, a trained model validated against separate data, right? That means that it passes, especially when you move from training data to validation data to testing data, right? You're going to use its performance in all three really to see whether or not it's ready for prime time. Okay, so the validation data though is just to like make sure that you're headed in the right direction. Once you feel like you've achieved that certain level, then the holdout data, the testing data, is what you use to validate that everything's ready to go into production. Now, here's some techniques, by the way, to kind of like mitigate overfitting and kind of maximize its ability to generalize, right? So we're going to talk about k-fold validation, simple holdout validation. We're going to talk about just briefly about leave out one, stratified k-fold, like the variations of k-fold. I will tell you that they're going to ask you about simple holdout, but they're not going to refer to it as simple holdout. They're just going to refer to it as split, you know, right? A split, really. And then they're going to talk about k-fold validation or cross validation. I don't remember a single question about leave one out cross validation, stratified k-fold cross validation, or iterated k-fold cross validation. I don't think they asked any questions about that. So anyway, you're going to see those words again because I just realized I just spit them out and you're like, Michael, I don't know what you're talking about. Simple holdout. Okay, so simple holdout is just basically when you split your data into multiple sets. There's like sets for training data, sets for validation, right? Notice they switch it to validation instead of evaluation, and sets for testing data, right? So you use the training and the validation sets, obviously, when you're actually training the model. And then once you're done with that, then you're going to evaluate the predictive quality of the model, right? Exactly what it states there. So, you know, the validation data is what you use where you're going to notice like major things that you're going to want to tweak and tune. And then when you feel like you're ready and there's less like tuning that you can do, and you've got the lowest minima possible, meaning that you've got the best predictive outcome, and this is based on, you know, consistency, right, and accuracy to a certain degree, although those words we'll have to talk about, right? But you've trained your model so it has the least amount of error or variance against what your actual data is telling you, right? In other words, the things that you want to predict are really close to reality from your data. Then you, like at that point, then you would test, like run the test data, right? So we talked about common splits, 80, 10, 10, 70, 15, 15. There's a couple of variations. Now, this is just simple holdout. So you can also use cross validation methods to compare the performance of multiple models. And the goal behind cross validation is kind of to help you choose the model that's going to perform the best into production. In other words, you could basically take your available data, right, and basically split it into however many folds you want. So K can be replaced by a number. So in other words, if in this particular case, we're doing 5-fold, right? Which means we've taken our data and we've split it into 4 training sets and 1 validation set. And then what we do is that we're going to train another model, same data set, but then what's going to happen is we're going to use another, and we might even randomize it just so we're clear, but we're going to use another set for validation, and we're going to continue to do that, right? And we do this for how many different folds we want to do, right? Now, someone tell me, what are the 2 most common, excuse me, what are the 2 most common fold numbers that we typically use if we're going to do cross validations? Does anybody know? Like, what are the ones that have been proven to kind of like maximize? Good, Michael. Yeah. So 10 is the other one, because obviously you can see 5 here, right? But 5 and 10, I believe 10 is preferred. Sometimes I've seen 8, right? And what this means is that this just means like how you like basically like split the data, right? So, so let's say if in this example we're doing 5, what you're doing is you're applying different models to different pieces of the validation data set in order to have some idea about how good the model performs. At the end of the day, you are using all of the data for training and for the cross the cross validation results are averaged to give us an idea. So in other words, you would average all the results of the model. And different machine learning models can be applied to the training data just to ensure that you can have a variety of models to compare the average or performance against, right? So again, here you've got 5-fold cross-validation. The available training data is separated into 5 different chunks. So for the training of the first model, you're going to use all the chunks except for the last, you're going to validate it, right? And then you calculate metrics. Second model, do the same thing, different set of validation data. Third, same thing. You do this 5 times, and you use all the training data with a different section used for validation each time. And then you basically test it on all the data points, average the results, right? This is a way of training, and it's particularly good when basically when like things are low, right? And Dakota, I'm going to answer that in just a second. When your data sets are like small. By the way, right, this is an 8-fold validation, right? Notice that we split the training data, right, into 8 sections, and we've got 8 models. So your training on each time is like, in a sense, your sets are smaller, your little training chunks are smaller, your validation set's smaller, but now you're doing 8 variations on it, you're going to average the results. Obviously, if we were to do 10, that's what it looks like, right? So Dakota, I hope that answers your question. The K, actually, just to be clear about it, the K usually refers to how you split your data set. Although often the model runs are the same as well. I've had debates about that. But typically, if you split it in 8, you might do 8 model runs, although I've seen people do 5 and 6 or whatever, right? So, and you're performing more tests. In generally between 5 and 10, right? Either 5 or 10. 10 seems to be the most common nowadays. 5 used to be super popular. 8 is probably the other number that I see more often after 10. One other thing to be aware of is that when you split your data, this is true of S3, by the way, in terms of performance, or DynamoDB in terms of performance. It's also true when you are ingesting data to train a model. If your data is in order, let's say it's in, like, for example, cardinal order as an example, or any kind of ordinal order, right? It's like, that's going to, for example, your model's going to get used to that structure. It's going to adapt to that pattern as it learns. And when you run your model against the test data, this pattern of sequential dating, because remember, it's going to adjust. Remember our original day 1. It is adjusting the weights of what it considers to be significant features. This is training it to look at those in a certain order. When you get your test data, it's going to bias it to like it's going to give weight to basically that kind of order, right? We don't want to do that. So this leads to a very different set unless you randomize it. Jonathan, can the 5, 8, or 10 diff models be the same models with different hyperparameters? They can. Be careful about it. Be careful about changing your hyperparameters. Like, just to back up for a second. Some people are like, hey, I'm going to change all the algorithms and stuff that I move in these models. You can do that, but I want you to be mindful. When you're creating models for testing and you're trying to figure out what the best success metric is, if you start changing a lot of variables, just like any good science experiment, you won't actually know which things led to the best outcome. And that may not matter if you're crunched for time and you just need to get it done because the business is leaning on you and saying, look, man, just experiment and give me the best. So be careful when you start mixing and matching a lot of changes at the same time. So whether those are model parameters or data hyperparameters, and then you start changing models, and then you start pre-processing and massaging your data set. Does everyone follow me for a second? Let me back up and clarify that. You're going to do things to the data before you give it to the model. You're going to choose, you could potentially choose different models and approaches, right? And then you're going to do different kind of model tuning afterwards. If every time you do a run, you start changing those inputs and outputs and everything, that can get problematic. So, because it's going to be too many variables that you've changed to know which one best influenced your outcome. Compare that instead that if you pre-process the same way, you use the same model every time, and then instead you told SageMaker to just run through a bunch of hyperparameter changes and give me the best outcomes, then the only thing you've really changed at that point is hyperparameters. You haven't experimented with changing your algos inside your model training, right? So again, just be cautious about that, is that make sure that you are methodical about what you change, because particularly an upstream change in data processing could change everything that happens downstream. Everyone follow me on that? Any questions about that particular comment? You can change it all you want as long as you track your changes and track the outcomes. By the way, SageMaker does do basically auto tuning. Basically, it'll experiment with the hyperparameters if you want to. So you can actually just let it figure out what the optimal is as well, Jonathan. Yeah, exactly. So Dakota, you're following me, right? Be very careful, because I've seen some people like, oh, hey, we're going to change the model every time. I wouldn't do that, right? I know it said it talks about, I think it's in the student guide, it says like you can run 10 different models. You could run 10 different variations of the same model, but be very careful about like, hey, we're going to try XGBoost and we're going to switch over to linear. No, don't do that. 10, if it's 10, then do 10 of the same model, maybe tweak some parameters, but probably not, honestly. Like just see how it does, and then run another set of 10 with tweaked and another set with a different set of parameters. Like try to keep this homogenized as possible, right? Because if you're going to average the results, you don't want to have wide variation in your model, because you're not really averaging the same thing. Yeah, Dylan, grid search is not, and by the way, that's on the exam. They're going to try and get you with that. Grid search is not available in SageMaker, but random is. So, and by the way, you can always manually set parameters as well. And Dylan, the reason that is, by the way, and by the way, for those of you who don't understand, just pause for a second. When we get to model evaluation, I'm going to talk about what this is, right? But grid search basically goes in and tests all of the available possibilities, right? And oddly enough, that does not as fast or as quick to converge against optimum predictive outcomes as if you do random search. So random search has been shown repeatedly to outperform grid for the same, for the same like time frame. The other thing is that if you're using a Bayesian optimization, that one's also a little better, because it's actually going to sequential. It's going to like learn from the last changes it made and just kind of keep. That's almost like reinforcement learning, just to be clear about it. It's like it's going to experiment and see if it can get to like the best possible outcomes. So those are the two that are typically supported. Grid search is not supported. All right, we talked about training data sets, so make sure that you do not have like randomize your orders, right? Don't keep the training sets in like any kind of like cardinal or ordinal order. Specific order leads to bias. Yeah. Okay. So let's say, by the way, we're talking about K, which is the number of folds that we have in our data, right? You can train the model more times effectively using all the training data, right? So a larger K, by the way, definitely means more time and more variation in the test error that you get for every subset of the data, because the size of the data is going to keep getting smaller, right? You got the same data set. So just follow me. You got the same data set. And every time you expand K, you could go from 5 splits of your data to 10 splits of your data to 8 splits of your data to 20 splits of your data, right? And so as you do that, the test data set is going to keep getting smaller and smaller. So you're going to get like more variation in the test error that you get for every subset of data. On the other hand, the data that you will use for training will be larger with a larger K. So go back to this. See how big validate is? Same data set. So let's say it's 1,000 records, right? 1,000 records, your validation size is going to be 200 here. If you split it 8 ways, right? What is that? It's going to be 125. Same data set, 1,000 records. If I split it 10 ways, the validation set goes down to 100, right? So larger K, more folds means more time and more variation in the test error, because your test data is going to get smaller. but your training data is going to get larger, right? So the bias is going to be reduced. So for a smaller K, we're using smaller chunks of the data and we're training the model fewer times. So if you do threefold, you're training the model fewer times, right? But your validation data is larger. So smaller Ks are going to be more biased because we're using smaller chunks of the original data set. So bias in the sense that there's a systematic difference between the true model, in other words, what reality is, and what our model is going to estimate reality is. And just to say this, like variance, we're going to talk more about bias in the following module. But for now, know that bias is where it thinks it's like basically the higher the bias, the more away from reality it is. The lower the bias, the more it matches the reality of our data sets, right? Variance, by the way, I like to think of variance as a little bit more like precision almost, is like how concentrated are your outcomes? Like how scattered are they versus how concentrated they are? So variance says like how variable are we? What is the range of predictions that our model is going to make? If you have low variance, by the way, you could be really good at making really tight clustered like predictions. If you have high variance, they could be scattered all over the place, right? Obviously, the idea is that we want low bias and low variance, but there's always a trade-off, right? So okay. Bottom line, right? If you use a smaller K for your fold size, you're gonna be more biased, which means you're gonna be like more off from reality, right? So we're gonna talk more about that. But again, just a reinforcement, 10 and 5 were the most common K folds have been shown the most effective. Some people will use 8 with other like cross-validation techniques, but 10 is typically the most popular. 5 was the previously most popular. So most people are centering around 10. They might go to 8 with some other cross-validation techniques. So remember, best practice. I don't know why this slide is here because I feel like it should have been after the other slide. But when it comes to like ordering your data, make sure you order it. I feel like this slide should have been back one. I'm not sure why that's there. So pardon me for the confusing presentation. All right. By the way, I'm just going to mention the other types. You are only going to be asked about K-fold, standard K-fold, right? You're not going to be asked about iterated K-fold validation with shuffling, right? You're not going to be asked about the other ones that I was mentioning at the beginning, okay? Notice, by the way, like based on what we know about K-fold, what's happening now is that you're taking your models, and this obviously is a threefold validation with shuffling. You're basically taking that data, you're splitting it up into 3 chunks. One of those chunks is validation data, and you're running your model 3 times. And then what's going to happen is you're going to randomize the order of the data, and then you're going to do the same thing again with the same 3 models. You're going to do the same thing again with the same 3 models. They're going to average all 3 scores. Now, back to Dakota's earlier point, you're not going to come in here and change off of different like core algorithms. If you want to do that, then make another like iteration set, right? Which is what we usually refer to it. Let's do another iteration set with a different model. And then you can average those scores with the scores you got from the previous iteration set. Anybody not following that? Because it's worthy of discussion if it doesn't make sense. Okay. Yeah. So there are a lot of other variations. I'm not really going to peel these back a whole lot, right? And leave out, for example, leave one out, cross-validation. The K is equal to N, right? So basically, bottom line is that every time we're going to leave out one data point out for testing, and we're going to use the rest in the training data. So this is used for really small data sets where it's almost like a variation where you're testing a data set, but you're going to leave one data point out, and that's going to be used for testing. You're doing another training data set, you're going to leave one point out, another training data set, leave one data point out, right? So that's just really for really small data sets. And they're not going to ask you about this on the exam, right? But just know that's where you take a training data set and you're going to take one data set, like data point out for testing, and you're just going to rotate through the different sets, right? Stratified k-fold, right? Which is stratified k-fold is mainly used when there's like seasonality, like swimsuits predictions, I'm trying to think of this, like putt bowling, that kind of thing. Bowling, did I say bowling? No, putt roller coasters, like Six Flags, that kind of thing. That's mainly where I've seen this applied. Stratified k-fold cross validation is basically going to go ensure for each fold there's some equal weight proportions on the data for every different fold. For instance, when you split the data, you might want to ensure there's equal representation of a certain target variable among the different folds. For example, seasonality. What season is it? What month is it? Yeah, and most of those seasonality, like tax season, like if you're dealing with like things that have fishing charters, right? That's another one I've seen where vacation analysis. Like for example, Key West is busier, they have a season, a certain time frame, right? Disney was the same way, right? Oh, I've worked for Disney in a long time. So forgetting to randomize your data, by the way, is costly and is a very common mistake, right? So, you can use scikit-learn in order to basically split your data sets, right? You're going to see this in the labs when we get to it. So main thing to remember about this section, just remember what k-fold validation is, and that it's a great validation technique. 5 folds, 5 models, 5 splits. Here, we're just going to walk through some visual examples of like holdout, for example, right? Now here we got 6, we've got 6 records, right? Really, we're splitting our data basically. What is that, like 16 and I don't know, 26% or something like that. And what's happening is that you're reserving half of your data set for training, right? Another like fraction, so 2/3 of the remaining for testing, and then 1/3 for validating, right? So you're going to be using the training and the validation data sets together to do the actual like model training, and then you're going to test it with the test data set at the end. Here's an example of 3-fold with cross validation. Now, I know your eyes probably just like melted, right? But I just want you to pay attention is that the target number, the 23, 24, 12, 24, 87, 67. By the way, what is that target column? Can someone tell me what the target column is? What's another name for the target column? Yeah. Yes. Good. By the way, at the end of the lab yesterday, I think if I remember correctly, yeah, you actually like rename one of the columns to target, right? At least I did. And I think when I was running through the flight delay, right? And I remember doing it on the other projects. So that's the label. So that's what we're like targeting. Notice here, what's happening is it's pretty much the same thing that we were doing over here, right? But notice that the records we're using for testing and in many cases validation, they're shifting around. So this is 3 folds. Now, remember in the previous example, by the way, our test data wasn't here, right? So just want to make sure that's clear, right? In 3-fold, we're going to be using the validation data and the training data. Here's an iterated 2-fold validation with shuffling. So in this particular case, so this is the first iteration, which they shouldn't be shuffling anything in the first iteration. Here's the first iteration. Notice it starts from 23 and ends on 67, right? Has the like target kind of order, if you will. As we roll out to the second iteration, they've randomized it, right? So now instead of being 23 to 67, we're now running 12 to 24. And notice that there's different sets of training, tests, and validate data sets. So we've shuffled our rows around. We shuffled our data around. Cool. Any questions about that? K-fold validation. They have iteration examples. They have shuffling examples. They have leave out iterations as well, right?
Question is this the only one with the first iteration and second iteration, or do all the k-folds have iterations?
No, this is iterated k-fold. So No, if it's just k-fold, it doesn't have iterations. If it's iterated k-fold, it has iterations.
Thank you.
Yeah, if it's iterated k-fold with shuffling, then they are randomizing all the subsequent iterations past the first one. So just remember those adjectives are qualifiers. It could be shuffled if iterated, k-fold, right? So. Do the number of iterations typically match the fold number? Yes, typically they do. But I gotta tell you, I've seen people not do it that way. But again, this is what most people do. But I would say experiment with it and see what you're going for there. But I've had like people who are deeper into the math be like, nah, we only need 3. We're doing 5, basically iterated 5-fold, and they're like, nah, we only need 3 iterations for that. I'm like, okay. Remember, most of the time I'm the guy who's like, okay, I'll do what you want. So, yeah. Hey, as long as it gives you the outcome you're looking for, I'm fine with it. I have argued in the past, and I've just learned to be like, yeah, okay, you know what you're doing. Okay. So this is just talking about how we split our data and hold out and making sure that we understand exactly as part of the pre-processing after we cleaned up all our data, what do we need to do that final data prep, right? That's really what they're clarifying for us. Now, here then we're going to move into model training. So during training, the machine learning algorithm, like in a sense, the prediction function, which is listed there, it's going to update a set of numbers, and they're referred to as parameters. Sometimes they're called weights. The goal is to update the parameters inside the math in such a way that our predicted outcomes, when we run data through the algorithm, the outcome is as close to possible as what I jokingly refer to as reality. This is also known as true output, but this is the data's reality. In other words, we've got a data reality in our data set because we've got a label, right? Because it's all supervised. And what happens is that we want this model to predict as close as possible to what the data reality as it can, right? So we want our predicted output, I'm going to use the proper terms here. We want our predicted output to be as close as the true output as it can be. So this can't be done in one training iteration, because the algorithm hasn't really learned how to tweak the variables, the parameters, the weights in the formula to shift the output closer to what the true value, the true output should be. Therefore, it watches the weights and the outputs from the previous iterations, and it's going to shift the weights in a direction that lowers the error in the generated output so that it's closer to true values. This process stops either when you've run the predefined iterations, right? Or when the change in error is below a particular target value. In other words, if you're not seeing the error improve, like the error being how close are you to reality? If you're training and you see the error go up, well, obviously some shit is going to happen, but you see it go down and you can't improve that error closer to reality, then it's going to stop, right? Now, when does it stop? How does it stop? How many runs does it do? You control that. The idea here is that for every successive iteration of the data run, the model needs to converge closer and closer to minimize that error. The training is successful when it can't do anything, right? Although, just to say this, the other thing that happens is that if the errors just increase or change randomly between iterations, there's going to be, you need to kind of relook at the model. Now, how can we best help the computer identify? So let's just take, for example, a linear regression model. Let's say you got 1,000 data points with one feature column and one prediction column. They are distributed as you see here, right? So let's call the feature column X, right? We're going to call the target one Y. Okay. So remember the training, the model's trying to find a way to map X to Y in the simplest way possible, right? It's trying to map how does this feature help me get to the target variable, right? And so what happens is that for a human being, you're like, this makes a lot of sense to me. I'm just going to draw a line kind of like in between these spaces because those predictions are really close, right? Like this is the line, right? This is the best possible fit for the data. Now, human beings can do this really easy, but here's the problem. A computer is basically going to need a couple of components to achieve this same results. It's going to need a way to measure that error, which they call a loss function, and it's going to need a way to optimize. Like what is the technique it's going to use to optimize the formula to get it as close to fitting as possible? The loss function, which is sometimes referred to as the objective function. Hold on 1 second. Yeah, thank you. The loss function, which is sometimes called the objective function, it's the measure of error in your model's predictions given a set of parameters or a set of weights. At any given moment of training, let me draw on this just a little bit. At any given moment of training, is this a glaring red? I hope so. At any given moment of training, and actually a line would probably be better. Let's do this instead. What's going to happen is that the model is going to produce an output prediction value using the weights that it has calculated up to that point in time. The output is almost going to always deviate from the true output to a certain extent, right? So what's going to happen is that the difference, right? The difference between the predicted output and the true output. So this is the difference between what the model is predicting and the data's true reality. That difference is the loss function. So the loss function is the metric used to update the weights after each iteration. Now notice here that what we're kind of like trying to get for is here, right? Does that make sense to everybody? We're trying to make sure that we have the closest predicted value to the actual data reality that we can, right? That's what we're trying to get to. Now we're going to talk about this more in model evaluation, but there are various ways that the loss function, also known as the objective function, can be calculated. The simplest form basically says, which is known as root mean square error, right? RMSE. This describes the standard deviation of the differences between the predicted and the true values. So you basically take the difference between the reality and the prediction, you square it, and then you average it across the whole data set. This is this equation here. By the way, do not memorize this equation. I mean, unless you're like into this, go for it. But this is not required, by the way, for either using SageMaker, creating models, or for the exam. So you're not going to see any of this on the exam. There's no math functions. This is literally just here for giggles, right? So that's what RMSE is, right? RMSE is basically, it's calculating the difference between the true output and the predicted output and averaging out, squaring it and averaging it out across the whole data set. So this is a mathematical function that lets you quantify, right, whether your model's doing well or whether it's not. And this is particularly for linear regression, right? Chris, I'm not going to talk about that just yet because we'll cover that in model evaluation. So that should be answered when we cover that particular section. But yeah, we'll come back to that question. Now, a common variation of loss function, right, is like log likelihood loss, or LOL, as my crazy team likes to call it. It's also known, by the way, as cross entropy loss. So with loss, instead of raw possibilities or predictions for each class, the log of probabilities is considered, right? So like for a binary classification, as an example, the formula for log likelihood loss becomes this equation. So you change it based on what kind of algo you're running, right? And breaking this down, it's like Y is a binary indicator, whether the class label is the correct classification for the observation for the prediction, and P is the model's predicted probability that the observation, like the categorization, belongs to that class, right? It's Karita, it's called cross entropy loss. So cross entropy loss. Let me type that out actually. Yeah. So to say this is like, that's great that we have math for this and that we have math for different classifications. We have math for regressions. That's great. That's awesome. Right? How does the error get minimized during the model training? How are the weights updated to achieve the minimum amount of loss in the model, right? In other words, how do you find the minima, right? This is where optimization techniques come in, right? Because we needed, because remember where we started is that we needed a way to calculate loss, and we needed optimization techniques to help us move that value along, right? So an optimization technique is going to seek to minimize the loss function, and what it's going to do, it's going to quantify, basically the penalty or error as a single value. So for example, this is like, the error is on the y-axis here and the single feature is on the x-axis. So just by looking at the graph, you know that you should always have the lowest loss possible at the bottom of that curve, right? Because remember, this is error. Error is at the lowest when you're at the minima. Are you following me? The left-hand side is error. You want that error to be as low as possible because that error denotes how far away from reality you are, according to the data set. Are y'all following me? Anybody not following that? Cool. Right? Because we want our models to be as accurate as they possibly can. They don't need to be perfect. They just need to be better, right? Preferably better than engaging a human workforce, but that's another thing. Depends on your business needs. So you just know that for a machine learning algorithm, it doesn't know this graph for a particular feature. So it needs a way to learn how to traverse to the bottom as well. That bottom, like where the minima is minimized, that's known as a trough. Sometimes it's called a global minima. Sometimes it's called the global trough. Just so you're aware. So how do you find that? How do you get down to that like point, right? And we're gonna talk about this in a second. And I gotta tell you, the minute I look at this, I hate this. I wish this was reversed. Just to say this, pretend for a second that instead of starting from the left and going to the right, that we're starting on the right, we're going to the left. Just pretend for a moment that everything about this is reversed, okay? Because this line is not. So let's say you're running an iteration, you're running a model, and see the gaps between these like data points? That's what's called the learning rate, right? In other words, I learned something and then I'm going to make some big changes, and I jumped over here and then I got here and then I got here and I was like, oh man. But then when I got here, my error started going up. I'm gonna make it sound like it's a human being, but it's not. It's just math, right? And the person's coming up, and they're like, hold on, we keep the errors going up. We're going in the wrong direction. Is everyone following me? In other words, the system thinks that it's at the global minima, because remember, it doesn't have this graph, right? It thinks it's at the global minima, but what happened is that it basically was like, oh, wait, hold on. Hold on. I'm now trapped in what I think is the bottom, but the bottom's actually over here. I couldn't find it, right? By the way, there's a couple of ways to kind of get around this. For example, you could actually do a large random kind of learning rate, by the way, and then kind of you can rescope it or refocus it on what you think are the lowest ones. So for example, these two probably had the lowest values. So then, right, you could like scope it down. There's ways to tune it to do that, right? That's one option. You can also just say, look, I know that this is the lowest, but I want you to keep going. And then as long as you don't cross this threshold, I want you to just keep going. Oh, wait, guess what? I discovered a new value right here that's lower. Everyone following me? In other words, there's ways for you to either force it to jump around a little bit so that it can actually discover where the lowest numbers could possibly be. In other words, there's techniques for approaching this. That's the main thing. Okay. We're going to talk about some of those techniques when we get to hyperparameter and model tuning. For now, just know that you might think that you've reached the lowest error possible. Oops. And what you actually are is you're at a local minima, not the global. So just be aware of that particular concept. Okay. Just remember the global minima is the lowest possible, like the lowest error possible that could be achieved with that particular algorithm, that combination, that data set. The local minima is just kind of a false minima in a sense of that it is a minima, but it's not the global one. It's not the lowest that it could achieve. Now, comparing all possible values is inefficient, right? Because remember, like if you know, okay, so this is a little bit like the conversation around grid search, right? Grid search runs through all possible combinations. So when you're running a tuning parameter job, what it does is it's running through every single variation it possibly can, every single one that exists. Now, this is mainly focused on the system, not on the weights, but it's going to run through basically hyperparameters. You could do that. How long do you think it would take for you to find the global minima if you were doing this, right? It takes a long time. It can be inefficient. It's going to cost you a lot of horsepower, a lot of time. You may not have, you know, the horsepower, the time, or the months to actually have this happen. So just be aware that, you know, you could actually run every single variation, but that might not fit your business needs because everything's about time, right? Now, so comparing all the possible values is to find the minimum is very inefficient, right? So instead, optimization use, which is at the heart of a lot of the ML algorithms. And so, for example, one of the simplest techniques is known as gradient descent. What happens is that it's basically going to, the loss function is going to be calculated at that step using the complete data set. And then the slope, which is the difference between the two data points between the, like known as the gradient, right, of the error curve is calculated using the loss function as value at the current point. So for gradient descent, the slope at any point may point us towards the bottommost point of the surface. Therefore, the weights are updated so that the error is going to move a small step towards the direction of the slope. Now, for example, let's say that you get here and you notice that you're doing the same change and you're like, holy cow, that thing went down a lot. Maybe I can do a bigger leap here because we're still going down. And then you go down here and you're like, wait, what? No, that's not going to work, right? Like errors out or whatever. And so what ends up happening is that then you're doing smaller and smaller as things flatten out, right? You're doing smaller and smaller as things flatten out. In other words, you get bigger Y's because you can see that in the gradient, in the slope, and you might like, oh yeah, we're going to slow down a little bit, but then we might go bigger as we flatten out, right? So this way, you're more likely, because for example, it would automatically notice that, by the way, here we are not going in the direction, right? If all of a sudden I'm here and I'm here and I'm here, and you're like, hold on, what's happening here? Why is it going up? We don't want that, right? Our slope, in other words, what it does is it tries to, in a sense, to kind of like calculate this kind of like graph, if you will. That way it does what a human being does. Is like we look at that graph and we're like, hey, by the way, this is the bottom. Or hey, by the way, you're here and now you're here and now you're here. You're going in the wrong direction. This is the right direction because your error is dropping. But now your error is increasing. You're going in the wrong direction. That's basically what gradient descent does. It's funny when you explain it like that, these big words, like all of a sudden they just make a lot of sense, right? We are optimizing for descent. That's the gradient that we're looking for. There's the minima. Now the learning rate, by the way, the learning rate is interesting because it defines the amount of change that it will update the weights at every like recalculation of loss at every iteration, right? So if your learning rate, by the way, is super high, the learning rate's too high, you're going to overshoot the minima and you're going to miss it, right? Now, if the learning rate's too low, conversely, you're going to take too long to approach the minima. Because let's say you have a month to do this. That'd be generous. Let's say you have a month to do this, and every time you make a run, it takes you, 10 hours. That would be a massive data set. Whatever. Moving on. Okay. So if it's going to take you 10 hours to do a run, and you've got a whole month of 730 hours, whatever, to do it in 10 hours to run, you can get 73 runs, right? But what if it takes you 100 because your learning rate is too small, right? To get to the minimum. Now, obviously you wouldn't do that. There's like ways around that, but that just is a gross over exaggeration, right? This step size, by the way, that it takes to update the weights, that's the learning rate. Okay. By the way, if the learning rate's too low, it never approaches the minimum, so it stays relatively underfitted, right? If the learning rate is too large, it generally tends to be overfitted. So another thing that happens is that as you get closer to the minima, some of the techniques, and you can do this manually, will also, by the way, like use a smaller learning rate, right? So you'll shrink the changes, they'll get more granular at that point in time. So the optimal learning rate basically depends on how flat or how steep the surface of the area is. In general, a small value of gradient indicates that the learning rate could be larger, which means that we can safely take a larger step down and not go over the minimum. On the other hand, a larger value of gradient indicates that the slope is steep. So we have to be careful because it's trending down, and we want to be careful because we don't want to fall off the cliff, right? So there's a couple of drawbacks, by the way, with gradient descent as it modifies learning rate, right? Is that you want to update the parameters only after they pass through all the data. So that's a drawback, because basically it's not going to update the value. Like it's not going to recalculate the slope and the loss and all that until after it's run through the entire data set. That could be really costly. That could be the 10-hour thing that I'm talking about. And by the way, it can't be used when the data set's too large to fit in the memory. So if you get a 16 terabyte data set, I don't know when's the last time you worked with a 16 terabyte system. I don't think I've seen one in a while, actually. I've seen it, oddly enough, I've worked with a couple of 24 terabyte systems. You can, that's not going to work. And by the way, it can get stuck at the local minima that we were referring to earlier, because it slopes down, right? So it can get stuck. By the way, you can force that by running. Anyway, I'm going to talk about that later. It's probably too much for right now. Now, there are, by the way, ways to minimize these drawbacks using different optimization algorithms that are based on gradient descent, but they're slightly different. Now, these are here just so you can be aware of it, right? There's some variations. So remember, gradient descent is only going to update the data after it's gone through all of it. That's known as an epoch. I've heard it pronounced different ways. I know I'm horrible at this, right? As far as the pronunciations go. Of the three variations, by the way, gradient descent has the slowest speed to find the minima, but it also has the fewest number of steps to reach the minima, but you could fall into the trap of finding a local minimum. Stochastic gradient descent, that's funny, I can pronounce that word fine. Anyway, stochastic gradient descent, or SGD, you're going to update your weights for every record, every data point in your data set. For example, if you get 1,000 data points in your data set, SGD is going to update the parameters 1,000 times, okay? With gradient descent, that wouldn't happen until you had ran through the entire data set. So SGK is going to lead to a lot more parameter updates, and the model's going to get close to the minima a lot more quickly. However, unlike gradient descent, it's going to oscillate in different directions, but the oscillations will always point towards the minimum because it's going to learn from every oscillation, right? It's not going to be a smooth approach to the minima. It's going to be jagged, but it's going to be trending towards the minima, okay? The other one is mini batch gradient descent, right? In this one, oh yeah, feel free to say it, I'm sorry. Another technique is called mini batch, right? So it's less noisy and erratic, but it's a little slower than stochastic, right? So stochastic gradient descent is the fastest by far. and you define a batch size, by the way. So you can define the number of data points that you want to run to update your parameters. I like mini batch. I just want to say this, right? Mini batch is definitely my favorite. Because gradient descent, and again, it depends on the total size of the data set, but gradient descent is, fun if you just want to like run it down. I like mini batch gradient descent because in that moment where I think it's stuck in a local minima, what I'll do is I'll increase the batch size to something ridiculous just to see what kind of data points I get as I vary it. And I'll run that a few times just to see if all of a sudden at some point in the same data set, right, I can see it like all the number drop down. And then I might actually start then stochastic, but I might do it at a different starting point in the data set. I might actually trim the data, like not trim the data set. I might set a different starting point. So stochastic, just remember this, by the way, stochastic will get you there quicker, right? Gradient descent is going to be the slowest, and mini batch gradient descent is going to be kind of middle of the road, and you can set batch sizes. So that's the main thing you need to remember for the exam. Keith, do you want to talk about simulated annealing?
Sure. My understanding is that like annealing from like a hardening steel,
Mhm.
you heat up the steel then cool it back down. So to avoid the local minima, you basically restart at random points somewhat regularly.
Yeah.
To get out of that little dip.
Yeah, so it's a variation kind of what I've been talking about the entire time, right? Is that simulated annealing basically will like basically explore your data through randomization to look for the lowest like loss value, the lowest error value. And that way it's kind of a little bit like random search versus the grid search, is that I know it sounds weird, but through that random exploration, you find a good starting point, and you might find like hit your local minima at a certain descent and slope. You'll hit your global minimum at a certain descent and slope. But if there's a difference, you're going to find it pretty quickly. And so that's a great then point for you to explore either side of that point. If the slope starts going up, you're going in the wrong direction. Slope starts going down, you go in the other. And so it can be a great way to do kind of like formalize what I was talking about by adding randomness into like how you look and evaluate and optimize your data set. Yeah, it's funny. I knew annealing because I was a blacksmith actually for a couple of years, and I knew what annealing was before I knew what the technique was. So good. Any other optimization techniques that people use? Okay. There are others. We're gonna keep it simple. Okay. You will be asked questions about this on the exam. They really love stochastic descent. So, but mainly just remember the speeds, right? Gradient descent could take a minute, get trapped in local. Stochastic's the fastest. If you do many batch, you just specify a batch size. The smoothest slope is going to be gradient. The roughest oscillated slope, as far as like how that's going to graph out, is going to be stochastic. So just remember that. Okay. Okay. Let's talk about running training jobs. The whole reason we're here. Wow, I must have a lot of energy today. I'm feeling better. Okay. So, we live in a world of code, so everything starts with an SDK, does it not? Everything starts with an SDK. I always run people who are like, hey, I don't want to code. It's like, man, I totally get it. I don't want to code either, right? We spent most of yesterday looking at code, messing with code, but it does make the world run. So let's do it. All right. So just note that you can initiate a SageMaker training session with either the SageMaker Python SDK, which I think is literally, if I remember correctly, like pip install like SageMaker. Or you can do it with the Boto 3 SDK for Python, which is pip install Boto 3, right? So, or Conda or whatever tool you're using. Okay. So here are your options, and they will ask you questions about how this kind of functions. And I'm going to talk about what kind of actually means. So be aware that you can deploy these algorithms using the SDK, a Python notebook, the command line interface, or the SageMaker console. I'm just going to say that the Python notebook is the preferred way to do it. right? The SDK is second if you're just doing a lot of programmatic stuff. But the CLI, by the way, is last. That is a horrible dumpster fire to run. It requires like 17 parameters. No. And the console is actually pretty decent, but again, you can't scale with the console. If you want to kick off like a bunch of jobs, you're not going to, you could do it through the console, but it's going to be so much more efficient, repeatable, trackable, version controlled, and all that if you do it either through the SDK in that example. By the way, you can still do it for a notebook. By the way, I've seen people throw their notebooks in version control, which cracks me up, but I've seen people do it. So, all right. So that being said, there's like, 4 or 5 ways to do it. Just so you know, everything in AWS can be manipulated through the management console, the web console, through the command line, or through some kind of SDK. The manipulation of SageMaker through a Python notebook is proprietary to SageMaker. No, most other services don't have that kind of additional 4th option, right? So there's the web console, the CLI or the command line interface where you just type AWS on the command line. And then there's the SDK where you import a library into your code and you manipulate it through code. And then that 4th option is Python Notebook. So just want to make sure you're clear. Python Notebook is the one that's like exclusive to SageMaker. The other 3 ways of either web page, CLI, or code, you can do that with any Amazon object. Oh, no. Sorry, Chris. Did it sound like I was making fun of that? That's not preferred, but I got to tell you, hey, at least they're putting it in version control. So I didn't have any complaints. I was just like, but I think it's great. Throw it in version control. Yeah. Version control tends to work a little bit better like with programmatic definition, right? In terms of like code, obviously, but I don't think there's anything wrong with throwing your notebooks in there. Again, at least you're checking them in, right? And then the changes can be tracked and you can put notes on the changes. So again, not knocking it, right? Code would just be preferred, right? And it's hard. Yes, that's what I was going to say. It's hard to interpret the differentials, right? So if you're note taking around the differences in the different versions of the notebook files, it's hard to reconcile it. You actually have to peel it out, load it, and really like to take a look at it. So not preferred. Whereas if it's just code, you can just look at the different, you can diff it right there and see the differences. But again, way better than not sticking anything in version control. So still like it. Okay. So here are your 4 options for scripts, algorithms, and models. Okay. So let me just say this. Containers are used behind the scenes when you use any of SageMaker's built-in algorithms, but you don't deal with the containers directly. So when you're using the built-in algorithms, you do not deal with the containers directly. You train and deploy these algorithms from the console or the SDK or whatever. These built-in algorithms are itemized and described in the algorithms topic that we were just looking at, right? 17 of them. I think there's more now, actually. I think there's 21. Inside that blue box, pretend that there's little containers in there that have your algorithms and code running in there. Second, SageMaker does provide pre-built containers to support things like everything that's listed there. MXNet, TensorFlow, Scikit-learn, PyTorch, right? Chainer. I don't know if I've ever used Chainer, actually. It also supports ML libraries, right? So if you want to throw Spark ML in there by providing pre-built Docker images. And you can use what's in the SageMaker Python class. I think it's called Estimator. You're going to see it actually today. You can supply the Python code that implements your algorithm and then configure the pre-built image to access your code has an entry point, right? So it's funny, you're using a custom script, but the supported frameworks like MXNet and all that PyTorch are provided has a pre-built Docker image. So you can supply like specialized code that implements your particular algorithm and then configure these pre-built images to kind of like support the framework. They'll ingest the code, if you will. You can also bring your own algorithm, right? So if you have additional functional requirements for an algorithm or a model that you developed in a framework, right? And you got your own like specialized framework for this, and it doesn't, your framework is so customized, it doesn't support the pre-built Docker images, then you can modify a SageMaker instance to satisfy your needs. So let me make a distinction here because I feel like someone, and please forgive me, with 21 of you, I don't always remember who asked the questions. Someone said, when would you use a custom script versus when you would like bring your own like container, if you will. And for my distinction, right, just to make sure this is clear, if you want to wrap code around an algorithm or just run your own custom algorithm, then you can just do a custom script on a supported framework. If you want to use your own custom framework, heavily customized, you want to bring that whole thing, that's when you're going to use your own Docker container and bring your own algorithm and your own framework. Now, by the way, it could be that you want an algorithm that isn't traditionally offered with Amazon, but the framework is MXNet or PyTorch or whatever. Then all you need to do is just create a custom script. It's just Python code, right? At that point. Now, but if you need to replace the framework heavily, then you're going to bring your own, and that's going to be the third purple option. Okay. Does that make sense to everybody? Was that Devin? Was that you? And I'm sorry, I didn't remember your name. I apologize. It was 2 days ago. I'm not sure that I was healthy. So I couldn't remember, but yeah. So that's the distinction. If you just need to change the algorithm, then just do a scripted base, right? Setup and just use the containers that they have for the framework. If you need to modify the framework and the algo, and it's just heavily customized and modified, you're going to want to bring your own container for that entire equation. Okay. Now, the fourth option is the marketplace. You can buy somebody else's third-party algorithms, right? Please have a relationship with these people that you buy off the marketplace, because you can just buy them without talking to them, but you don't know what's in there. I'm not saying they're going to do anything malicious. This is all running on AWS, but maybe they siphon out your data. You don't want that. Do I sound paranoid? I apologize. No one has ever reported any problems like that, but probably because people like me who teach this are saying things like that. Like, watch your sourcing, right? If you don't know the company that you're pulling from and it's some random group, that maybe looks a little sketchy and doesn't have a great website, don't be pulling third-party algorithms out, okay? Because you don't know what's in that container. So make sure it's either an open source project that's been verified, or it's a company that you can verify their existence. Do I sound paranoid? Yeah. Keith, I do not know the answer to that, actually. Let me take that down. Oh, I stole all my pens. Hold on a second. Yeah, here it is. Let me take that down really quick. I don't remember. I don't think I've ever done any Pi to IP and YMB conversions to notebook conversions. Yeah. By the way, do you work with Databricks, Keith, by the way? I love them. They've been around for a while, actually. Yeah. They made EMR easy, by the way, back when EMR was hard. So I really like them actually a lot. When EMR the service, not the MapReduce or the Hadoop framework. Cool. Yeah, let me find out. I'll dig that up. So. Okay. There are containers all over the place. Here's the bottom line. They're going to ask you a question. This is going to be on the exam. They're going to ask you a question and say, you want to run your own custom algorithms, and they're not going to offer you this script on a supported framework option. In the answers, they're going to say, pick the 2 out of the 5. And 3 of those answers are going to say, you're going to call, like one of them is going to say, you're going to call Amazon support and edit the algorithm that's standard and included with the SageMaker algorithms. Or they're going to say something like, you can go in and edit the built-in custom algorithms. Let me make sure that I'm super clear on this. You cannot edit the algorithms that are built into SageMaker as they are run in SageMaker. That being said, you can go to the open source version of like the SageMaker XGBoost Docker container, pull that down, modify it, and then run it into your own algorithm and framework. But bottom line, you cannot customize the built-in algorithms for SageMaker. If you want to change them, you either need to do option 2 and do a script and wrap some code around it to change the algorithm, or you need to bring your own Docker container. Does that make sense? Anyway, is that not clear to anybody? From what I've seen, almost every built-in algo, first of all the built-in algos are open source, so you can actually go find them on the open source project pages, the respective project page. But Amazon, in most of the cases I've seen, actually takes their sourced container, for example, that contains XGBoost, and you can go download that container and modify it. So not only are all the algos open source algos, but Amazon publishes their containers for you to download and use for your own custom frameworks and algos. I like I say this, like, I have mixed feelings. I work indirectly for Amazon because I work indirectly for a partner who indirectly works for AWS, right? And God, like they're just a conglomerate of startups, right? But I gotta tell you, they are trying actually to give back to the community, but they do also run a business, so they're pretty draconian about how they treat other businesses. So, I always have mixed feelings, but they do try to give back to open source. So you'll find a lot of this stuff is all open source. So is it self-serving? I don't know. It could be.
I've got a quick question then.
Yeah.
So in that case that you were saying, where you, if someone was to download the Docker image, modify it, and then want to run it, then that's going to fall into the purple use case here, the third one. Correct?
Mhm.
Okay, just want to make sure.
Yeah, that's if you download the container, run it down. If you just want to use an existing framework and just wrap some code to change the algorithm, you could change the algorithm without running your own Docker container. In this particular case, like you also could change the algorithm alone just by doing either one. You could change the algorithm through a script, which is the blue. You could change the algorithm through your own Docker container. You have to use your own Docker container if you're going to change the framework. And hopefully the picture is clear about that as well, right? Notice that you were okay running whatever code you wanted to change the algorithm, and that was totally fine. But the minute you started messing with the framework, you had to go to purple, right? So hopefully that was clear. Okay. Marketplace. So the marketplace is a place, by the way, where you can go grab a bunch of stuff. What do you need, right? So this is a curated catalog of a bunch of packages and algorithms. So yeah, there's not much to say about this in that they're really easy to use. One thing to be careful of is that sometimes they'll charge you a subscription fee. It's going to go to your Amazon bill. You're going to click an agreement that says yes to it. The fees aren't going to be crazy, but sometimes they'll charge you a fee that's just a flat fee. Sometimes they'll charge you a fee where you get charged for the training time. So you get charged by SageMaker for the training time, and you get charged by the company for the training time. Does that sound like a good deal? Not to me. So anyway, just be aware of that. So make sure you when you pull something from the marketplace, obviously have a relationship with the vendor and know what they're going to charge you. Okay. Okay. Earlier, like at the very day one, we talked about weights or parameters, right? Or also like weights, bias, that kind of thing. So just to be clear, right? Hyperparameters, because we're not here to talk about parameters. Parameters are the things that the algorithm is going to change weights wise, right? To optimize towards a minimum amount of error, right? Minimizing loss. Hyperparameters, right, are basically external to a model and can't be estimated from the data. Hyperparameters are typically set by humans, although SageMaker will allow you to run like an auto experiment, like auto tune, if you will, where it basically goes through and experiments, right? So think of hyperparameters as the knobs that you use to tune an algorithm to improve its performance that are outside of the data set. They're not about the data set. They're about how the model functions. Some of them, by the way, are model parameters. Some of them are like other parameters. Like the learning rate, for example, is a hyperparameter. How much am I going to change, for example, the rate of change in my weights as I experiment to find the loss function? And remember, like the learning rate hyperparameter, for example, can have a big impact about how you converge to the global minimum, or whether you get stuck in a local minima, or whether it takes forever, or whether it goes really quick, right? That kind of thing. So we're going to talk about hyperparameter tuning more later when we get to model evaluation. I just want you to be aware that it's there. All right, we're on the last few slides, by the way, and then we're going to take a break. So I just want to acknowledge that, I've been talking for an hour and a half, and you've been listening for an hour and a half, and you've been participating for an hour and a half. So So notice that these images that we keep, these Docker images that we keep referring to, they are hosted in what's called a container registry, a container repository. That image is what it pulls by default when you say like you want to use like linear regression, right? With like, let's say XGBoost, right? XGBoost, like if you're using that, then you're going to pull that image off of Amazon's internal Docker / container registry. And that is going to get pulled into your like the instance that you specify, because you're going to specify a virtual machine that's going to like do all the number crunching, do the processing. It's going to source the data from S3. Now, someone mentioned the other two possible sources that we could pull data from. Give me one of them. Yes, oddly enough, yes, you can't pull data from Kinesis, but to be clear, you can't pull data from SageMaker directly into Kinesis. You have to land in S3 first. Yes, you could pull from Redshift, but again, you can't pull directly from Redshift. You have to pull from it from S3. And again, EBS is just a temporary file system. So FSX is one of the network file systems other than S3 that you can pull directly from for your instance. What's the other network service? EFS. Okay, so let me be very clear. You can actually pull indirectly from any data source you want, but you can only pull directly from S3, EFS, or FSX. So let me make sure everyone's super clear on that. If you want data from Redshift, it has to get into S3, EFS, or FSX first. If you want data from Kinesis, it has to land in S3, EFS, or FSX first. They're going to test you on this. They're going to say, where would you source your data if you're running a SageMaker instance? And they're going to list all the data sources. And you're going to be like, yeah, of course I want the RDS customer data. Of course I want the Kinesis real-time like clickstream analytics. I want that. But they're going to fool you because you're not going to be able to directly get there. What they're going to say, you're going to take Kinesis Firehose, which is going to dump the data into S3. Then you're going to start a SageMaker instance and you're going to ingest the data from S3. That's the right answer. If it says you're going to start a SageMaker instance and you're going to pull directly from Kinesis, wrong. If you're going to say I'm going to start a SageMaker instance and I'm going to pull directly from RDS, wrong, right? Just to make sure that we're clear about it. So there should be no confusion, hopefully. Your sources for a SageMaker instance are S3, EFS, or FSX for Lustre, L-U-S-T-R-E. The only reason I say that is that FSX has 4 flavors. Lustre is one of the flavors, okay? And in case you don't remember that from yesterday, Lustre. Oh, hold on. Lustre is spelled this way. RDS Kinesis Firehose to S3 instance. So no. So to be clear, actually, Christopher, oh God, that is such a great question, by the way, because this is going to be on your exam. So Kinesis Firehose can really only pull from Kinesis. So Kinesis Firehose is for Kinesis pulls. So we're clear. It's Kinesis for Kinesis. If you want to pull from RDS, then what you would do is you can use what's called the data pipeline. And you could also use DMS for that, but data pipeline is probably what we're going to be talking about. And data pipeline will pull from any AWS service and then dump it into S3. Here's the catch, Christopher, and for everybody else as well, is that if you want to, you can actually pull from an on-premise database. And please, everybody, make a note of this. If it says on-premise database, there's only one service that will allow you to pull from an on-premise database and dump it into S3. And it's called DMS, the Database Migration Service. So the Database Migration Service is what you can use because it'll run an agent on an on-premise database and then dump it into S3 if you want it to. Now, here's the cool thing. DMS will also do RDS databases. So DMS will also allow you to pull data out of an RDS database and in there. But I just want to qualify that because this showed up on my exam. It's like, how do you pull data from an RDS database? And the answer, I was like, oh, well, I'll just use DMS for that. But data pipeline was there and I had to answer data pipeline because data pipeline can also be used for it. But if there's an on-premise SQL database, you can only use DMS for that, okay? Devin, to be clear, training jobs use training data. So we're talking about where to source your data for the job. So it has to be S3, EFS, or FSX. So I just want to make sure I'm not missing what you're asking. Or
Hey, it's Devin.
yeah, clear it
So
out for me.
I was asking based on the context of the slide. So it looks like, yeah, you're pulling a training image and then you're pulling training data. So is
Yes.
so it's the same restrictions, like it's got to be S3, it's got to be FSX.
Oh, yeah. Good. So let me be clear. Your training data comes from those three sources. Your training code has to come from a Docker image.
Okay.
Yeah.
Gotcha.
Yeah, that's a great distinction. Your training code, whether you bring your own, use a built-in standard, it has to come from a container registry. You have to use ECR or something like ECR to pull your image down. But the training data always comes from those three data sources, typically, like S3, EFS, and FSX. Yeah, good. That's a good distinction, actually. Cool. Other questions?
This is Christopher. I'm still a little confused on the order that we pull stuff into in S3, for example. So if you start with some generic data source, data lake, I mean, which services do you use to eventually get it into S3 so that you can pull it into your instance? In what order?
Okay, good deal. So for example, if you're running a data lake in AWS, the underlying component of that data lake is going to be S3. So typically, so you would just pull directly from S3. If it's in any other data source, right? And let's talk about any other database, you can either use the data pipeline tool, you could use Glue, which is another tool that you can use to run data jobs, or you can use DMS. Those are the three possible services that you can run to pull data out of any other data source into S3, right? And you could also, by the way, in some cases, dump them onto EFS and to Lustre, but typically S3 needs to be the target, and then you can transform it up to EFS and FSX if you want to. But those are the three main services. Now, so here's what I'm going to answer for that is that I promise you, if you run through the practice exams, they will make sure that in your mind, you understand which things you have to use in order to pull from which sources, right? The only real distinction though is that if you're going to do any kind of like transformation mid-flight, you're probably going to use Glue. If you're going to talk from one AWS service into S3 and you have no on-premise functions and no ETL, you're going to use the data pipeline. If you have on-premise and you have no ETL, you're going to use DMS. Now, just to be clear, you can run Glue on data that's in S3. So it's not like you can't use Glue after you've gotten the data with DMS or after you've gotten the data with the pipeline, the data pipeline. You can still run Glue jobs on data that's inside of your S3 buckets to transform the data. But DMS is used for on-premise. The data pipeline is used for anything that's in AWS exclusively. And again, you can use DMS for services, but typically when they ask you questions, DMS is only for on-premise databases. So between particularly those two tools, but also Glue, you should be able to source from any data store, any data lake, any third party that you want to. Does that, hopefully that clears it up. If it doesn't, please ask me clarifying questions.
So if we were pulling from like an on-prem database and we wanted to do some transformations, then we would need to go from DMS to Glue, or how would you probably do that?
Yeah, so in that particular case, because it's on-premise, you'd have to dump it into S3 first and then run the Glue job, right?
Oh, okay.
And yeah,
Sure.
yeah, and typically that's how you do it, is that you get it into S3 first, and then Glue will run it and ingest it and hit it. So and you can trigger it, by the way, so that an automatic job, because DMS can dump data continuously, can data pipeline, meaning it can just take any on-premise system and just continually dump data into your S3 data lake or S3 bucket. Doesn't have to be a data lake. And then what will happen is that after a certain time period or a certain threshold, you can automatically trigger your glue jobs to do some kind of ETL on the whole thing. But typically you're going to dump it in S3 and then you're going to have glue ETL it. But the only other thing that can happen is that sometimes you can feed directly from Kinesis into glue, but most of the time you're going to jump out of S3. Lambda can be the trigger for glue, just to say this, Chris, but S3 can also just trigger a job. So, but I like to say this. Hopefully I've given you enough information to kind of get the general idea. Your practice labs are going to make sure you know this. I promise you, especially if you're actually like learning what the wrong answers are. It's going to make sure that you understand 100% what the transformations are. I assure you, right? It's going to do it. And if you're running the thing, you're like, I really don't understand it, then you need to deep dive into it a little bit. But those are the general tools: DMS, data pipeline, and glue. Glue is used for ETLs, mainly out of S3. DMS is used for on-premise databases, but can be used for online services in AWS. Data pipeline is used exclusively only for services that are in AWS to move data around, but particularly to S3. Okay. Okay, this is the code, right? Then here they're deploying PCA, right? Notice that all they did was import Bodo and they imported SageMaker. Notice that there's the estimator that I was talking about. Hold on a second. There's the Bodo 3 session. Oh, you're looking for the region name. There's the role, there's the instance count, there's the size, there's the output location, which typically there'd be more information there. And the SageMaker session is just blank defined. That's fine. And then we got hyperparameters, feature diminishment, number of components, subtract the mean. Okay. Yeah, that all looks legit. And then the last thing is you're going to run pca.fit. So you're going to call fit from the SageMaker set. And then what will happen is it'll basically just run through the training data. So a couple things here that are weird. Notice, first of all, there's a session size. Notice that you've got some hyperparameters, and notice, by the way, the algorithm mode. So just know, by the way, that almost all of the algorithms have some kind of mode attached to them, like, you know, soft multi-mac, like there's tons out there. For the purposes of the exam, I cannot offer you which things to memorize because there are so many parameters, but you probably need to skim all the like particular like algorithm modes for the algorithms. So at least you just have some high level idea, right? The training tests, the practice exam, study exams, by the way, will also teach you about some of these modes that you want to know about. Okay. That's it. Right. So fit, by the way, is the method that actually does the training, right? So this is a SageMaker create training job API, and it starts the training and then uses the specified input data to send to the create training job request. Pretty straightforward. Okay. Okay. What just happened there? There's a training job demo, but I'm going to hold off on that for just a second. We're going to come back around to it because I really want to give you guys a break, actually. So, and you're going to see this actually in your labs. So summary here is that you want basically two factors to consider when determining which algorithm, right? What are the two factors? What's the business problem, right? And then what's the ML problem that you're trying to solve, right? Is it classification, regression, recommendation, topic modeling, embedding? Are you detecting anomalies, right? What algorithms are going to use? What are the two most common format? Actually, let me ask you a better question. Other than CSV, what did I say were the two formats that were used for Athena, which is an SQL reader for S3, and the format that I said was optimized for SageMaker? Does anyone remember what I said was optimized for Athena as far as like file structures? Anyone remember that one? Yeah, Parquet, good. And Matthew, you put Protobuf in there already, so that's the one that's for SageMaker, right? Record IO protobuf. Okay, good. Good. Remember that. They really love protobuf for SageMaker. And why? Because it performs faster. It does. Okay. What is the problem that we're going to avoid by splitting the data, right? If we evaluate a model with the same data that we used for testing, sorry, for training, sorry, what does that cause? Yeah, memorization overfitting, right? It avoids overfitting. Good. All right. Give me a few techniques for mitigating overfitting and maximizing generalization. Give me any of the techniques that we talked about. Give you a keyword. Okay, good. Leave one out, valid cross validation. Make sure you say the full thing, by the way, because it makes a difference. So leave one out, cross validation, right? We've got k-fold validation or cross validation. What is it called when we actually just split the data into multiple sets? What's the official name from we just split our data into different sets? Someone remember that? Yep, simple holdout. Good. But why? Mainly, and train test split, I think, is also valid, right? But remember that test data that you hold is at the very end is also called holdout data. So that's simple holdout validation. That's the old term. We used to call it holdout data, obviously tested. Which of the, by the way, of the cross validations do we use when there's seasonality or like strong subgroups in a small proportion of the data set? It was a specific type of k-fold cross validation. Yeah, so stratified. Perfect. Okay, good. All right. By the way, which is the one that allows you to do different like model sets, but also shuffle the data? Which one was that? Give me an idea of the k-fold validation. So iterated covers iteration. Which part covers the randomization? Because iterated k-fold alone doesn't randomize the data. What do? That's right. You shuffle the data. Perfect. Good. Good. All right. Okay. What does the model change as you feed it training data, like after every epoch, or in some cases after, like, what does it do? Parameters, weights. That's right. Good. It's going to change the weights of the significance of the features that it's aware of, right? Good. What's the name of the technique of kind of evaluating parameter changes against loss? What is the name of one of those optimization techniques? Right? Good. It was gradient descent. What are we chasing when we use an optimization technique like that? What are we trying to get to? What is the part? We're trying to get to the global minima, right? Or the global minimum, sometimes minima, right? It's the technical correct term. Tell me the type of gradient descent that allows you to define your particular sizes. Mini batch, good. All right, so what was the one, and again, wow, this was just a minute ago and I can't believe, maybe it was Keith. What was the one where we were talking about a type of optimization technique where you actually like start at random points inside of the data set? You're exploring random weights, sorry, inside of the weight values. My apologies. It had to do with blacksmithing it, right? Yeah, good. Simulated annealing. That's good. Good. All right, which of the gradient descent ones was the fastest, right? As far as like updates. Good. Stochastic, right? Because it did data points. Good. Okay. So why are hyperparameters significant? What do they do? What do they govern? What do hyperparameters govern when you train a model? What are you tuning, right? Yep. Okay, good. What are you tuning when you change hyperparameter, right? You're tuning how the model trains, how it behaves, how it learns, right? And that's exactly right, Dylan. the rate and manner and other aspects of how the model learns, okay? So when you choose the appropriate hyperparameters, remember, you can really impact your model's behavior. Now, if you're doing k-fold validation, by the way, are you going to wildly tune all the hyperparameters when you're running, for example, through an iteration? Please say no. Please say no. Yeah, not if you want your average to mean anything. Can you methodically change the hyperparameters? Of course you can. Of course you can. Just don't go in there and put a bunch of wild variations. Change a few things in one iteration, change a few things in another iteration, track what you're changing, and then do a comparison, right? Good. Okay. A training job sources from two things. And I want to talk about this generically. I don't want you to give me the technologies. What are the two things that SageMaker uses to create a training job? What defines a training job? What do you need? So I'm gonna give you one, right? And I think you guys can figure it out. But you've got data, right? Which is what I see the answers coming in, and you've got the actual like model code itself, right? So you need data and an algorithm, right? And probably some wrappers around the algorithm, which is really where that comes in, right? Okay, now what are the technologies what is the technology that provides the training code for the training job? Where does that source from? Good. ECR. Generically, you could call that a container registry, just so you know, because Amazon loves the word elastic. That stands for Elastic Container Registry. Follow me, okay? All right. And then if you want to get your training data, SageMaker can only pull from 3 key sources directly. What's the primary source that pretty much everyone uses? Dakota, answer that for a second. Yeah, S3. All right, let me answer that for a second because there were 2 questions here. Keith, can you use Fargate containers? No. Can you pull from a CR outside of Amazon? I've been told that you can, but basically just to be clear, what you do there is you actually attach ECR to the external registry and pull it in. But I've been told that you can't actually pull directly from an external registry. I've never done that because every company that I've ever done this work for will not allow you to pull outside of the VPC. So you can't source even across a corporate network. But ECR, you can pull from the container registry, another container registry, pull it into ECR, and then ECR can consume it. So you can. I've never done it because all the SageMaker instances I've ever launched here in the last, like, I would say 2 years have all been super private because people are really concerned about security when it comes to access to some of this data, even though it doesn't have PII in it, right? Remember, data is the new oil, right? We don't want our oil stolen. It's a horrible analogy. Can we just say data is like the new gold or the new oxygen? Anyway, moving on. So yeah, so yes, you can pull from a container registry outside of Amazon, but most people will use ECR as a stopgap. Keith, just to go back to the Fargate container thing, is that for those who don't know, by the way, and that's a really solid question. The reason that's a solid question is that ECR Fargate and EKS Fargate are both container services, but you don't have to manage the virtual machines underneath them. And the reason this is significant, and thankfully SageMaker doesn't do this, because if it did, it would be prohibitively expensive to run SageMaker. But most of the time when you launch a virtual machine, you pay for the capacity that virtual machine is consuming. SageMaker doesn't do that. They charge you for the amount of time you're training. So Fargate is a way of running containers where you only pay for the size of the container, which is kind of what SageMaker is doing already. They're just not they're not calling it Fargate, right? Because you're still not managing the servers. So in a sense, Keith, I said, no, you can't use Fargate because that's proprietary to ECS and EKS. But in a sense, you are using Fargate because we're not managing the virtual machine really at all, right? So in a sense, you kind of are, but the answer is no, as far as like, can we use ECS or EKS, right? Just remember, Fargate is only associated with those particular products. And by the way, for ECS and EKS, for those who don't know, that's the Elastic Container Service and the Elastic Kubernetes Service. Those are orchestrators for running containers for other purposes outside of machine learning. But I say that, I can't tell you how many EKS clusters I've run that have machine learning on them. So, but SageMaker just makes it easier. Cool. Let's see. Is there anything else for us to talk about here? Do we feel like we recapped that pretty well? I think we did a pretty good job, right? Here we are 2 hours later. We just data dumped a bunch of information. Does anyone have any questions? I don't know about you, but I think it's time for a break. All right. So here's the deal. It's 10:28. So I'm going to give you a little extra because you trooped through me with this. So let's come back at 10:50. So that's literally 22 minutes from now. Okay. So 10:50, let's come back. I'll put up a timer. And then I believe we're going to do a little checkpoint and then we're going to roll on to evaluation. Okay. Cool. All right. We'll talk in a bit.